Hi people, let's talk about an oscillating mass on a spring. We're going to do this in the context of a lab. You all have data that you have collected and you're going to process. So what we did was we let different masses hang and oscillate from this spring, and you should have made measurements of period t the time for a single oscillation. It's an amount of time. It should be measured in seconds. All right? And with a little adjustment, what you can find is what we call the angular frequency of this oscillation. Angular frequency is really the same thing as angular velocity, which we used to say is angular displacement per unit time. Well, we can talk about a special amount of time, the period, and in a special amount of time for, well, one full oscillation, what we call the angular displacement is 2 pi radians, right? A full oscillation. We're not saying that this mass goes in a circle, all right? But what we are saying is that if we go back a couple of slides, yeah, here's up on the top, here is literally the function of the object's oscillation. It, well, over time follows a cosine curve, all right? And this sort of by definition is 2 pi radians, okay? Or a full cycle encompasses 2 pi radians worth of angular displacement. Okay, so now that we've measured period, we can calculate omega for each mass. So you probably have something like T and M. You should do omega. I don't know what this column is for. Use it as you see fit. And then what? All right, well, here's what. Okay, you are going to you're going to process your data. All right. Now, if you plotted raw data, what we really want to, what it's most appropriate to look at is, or to say is that this system's angular frequency depends somehow on its mass, right? It also depends on the spring, and in particular the stiffness of the spring, K, what we call the spring constant, all right? But we kept K constant, all right? Now this graph, if you were to plot this omega versus M, would look maybe something like that, all right? And what I'm going to say is just don't bother. And the reason we're not going to bother is because we would plot raw data and look at that graph and say, if we didn't know what the relationship between omega and mass was, what we would do is maybe plot that graph, look at that shape, that general trend, and say, well, what's that? What does that suggest? What kind of relationship does that suggest between omega and mass? Well, we already know what the relationship is. All right, you might have to go back a video, but for a mass on a spring, what you need to know is that angular frequency is, you can derive that it's equal to the square root of K over M, where K is the spring constant and M is the mass of the object hanging from the spring, or doesn't have to be hanging from, attached to the spring. All right, so what you need to do is you need to still put omega here. So we're going to make this data useful. All right, you're going to put omega there. Then the question is, what goes here such that you get a straight line? All right, now we make straight line graphs because the slope, in many cases, is going to be of some value. And in particular, you're going to use your graph to find spring constant. All right, now here's the deal. You've got to take this expression, and you've got to turn it into something that looks like that. All right, I'll give you a hint. Look, we've already got part of it. It's that omega equals, and yes, omega is on the y-axis. Well, that's good. All right, so what you've got to do is take this thing, turn it into two terms. one for slope, and one for the thing that goes on the x-axis. And, well, I mean, the answer is right there. You just got to break that up the right way to say, well, maybe the slope of this thing isn't going to just be k, but maybe I can use the slope to find k. All right, now, we did vary mass, so the thing that goes here has something to do with mass, but this expression definitely does not say that omega is proportional to mass, right? It just doesn't say that. That's not true. But omega is proportional to something having to do with mass, something that goes in this blank. And then the slope is the thing that's left here. So I would take this and isolate everything that has to do with mass and put it there. And then put the rest of the stuff here. And that stuff is the slope. And then, if you do this right, you're going to get a nice straight line graph. Find 2 points on your line. Calculate the slope of that line. And then use that to find k. Right? If you're saying, I just don't get it, I don't understand, you know what? There's the answers are out there. Look for them. You'll find them. Okay? If this isn't enough for you, then do more. Okay? Go and search. Go and find. Okay? For a lot of you, you'll be able to get it. Okay? Now, what you also have to do for my people is there is a lab posted in our shared waves and oscillation folder that tells you all the other stuff you have to do and questions you have to ask and narrating parts you have to do or questions you have to answer. All right, so you've got some other steps to some other blanks to fill in, but the big deal is, how do I get this straight line graph from this expression? All right, and the bottom line is you got to turn it into something that looks sort of like this. Okay? Okay, I will see you when I see you next, and you will have a completed lab. All right, bye.